Hi, I'm Miki Nakajima. I'm an assistant professor at the University of Rochester. I would like to thank the organizers for inviting me to give a talk. It's my great pleasure. So first, I'd like to introduce my virtual background. This is an image of my office, and this is the moon, and this is the Earth. So these are spray painted paper lanterns we created about a year ago. So I thought this would be a perfect background for today's talk, so I picked it. Nowadays, nobody visits my office, so I'd like to welcome you all to visit my virtual office. Okay, let's begin. Today, we talk about origin of the Earth and Moon and discuss its implications for Earth's environment. So why is it important to understand the origin of the Moon? Because the origin of the Moon is the same as the origin of the Earth. So the moon formation was the last step of the Earth accretion phase. And also it defined the initial condition of the Earth. So by understanding the moon, we can better understand the Earth. Presence of the moon affects life on the Earth. The ocean tides are partly caused by the moon, and ocean tides are very important for biological activities on the Earth's surface. And also, the moon tells us the impact history. Since the Earth has plate tectonics and weathering, the impact craters have been eroded over the years. But this is not the case on the moon's surface. Therefore, the craters are well preserved. So by looking at the moon, we can understand the impact history of the moon and also the Earth. This also has a huge implications for life. As everybody knows, the dinosaurs got killed by a huge impactor. So this is also very important. First of all, I'd like to introduce historical hypotheses of the lunar origin. The first one is the capture hypothesis. So according to this hypothesis, the moon was an asteroid and it was gravitationally captured by the Earth. The second hypothesis is the condensation hypothesis. So according to this model, the moon and Earth condensed from the disk simultaneously. The last one is a fission hypothesis. According to this model, the Earth was spinning very fast, and the outer part of the mantle got stripped off and became the moon. But these hypotheses were challenged by Apollo findings. As you all know, we went to the moon and we explored the lunar surface and brought back lunar rocks by the Apollo missions. And now we understand the moon so much better than before. So first of all, now we know that the moon has a very small iron core, around 300 kilometers. So this has been measured by seismic stations on the lunar surface. And we also know that the moon is depleted in volatiles such as potassium, rubidium, and sodium. And we also know that the Earth and moon have very similar isotopic ratios. So this has been confirmed by many isotopic systems, including oxygen, silicon, tungsten, and many others. This was quite surprising because we thought that each body has its unique isotopic signatures. In fact, Earth and Mars have very different isotopic ratios. So originally we thought that the Earth and the Moon have very different isotopic ratios, but that was not the case. So this was a very surprising result. So the volatile depletion and isotopic similarities have been found through analyzing lunar rocks. The Apollo findings challenged the historical hypotheses. So first of all, let's focus on the capture hypothesis. So in this case, you'd expect that the moon is pretty much an asteroid and it should have a decent amount of iron. Therefore, it cannot explain why it has a small, the moon has a small iron core. And also, the asteroid should also have a decent amount of volatiles. Therefore, it cannot explain why the moon is depleted in volatiles. And it cannot explain the isotopic similarities either, because each object would have a different isotopic signature. And additionally, dynamically, it is challenging to capture an asteroid by gravity of the Earth, especially an asteroid like the moon. The moon is a very fractionally large object to the Earth, and you have to decrease the velocity of the asteroid quite a bit to capture, but it turns out this is very challenging to do so. The next model is the condensation hypothesis. So in this case, you'd expect that the composition of the Earth and the moon should be quite similar. Therefore, you can explain the small lunar iron core or volatile depletion. Perhaps it might be able to explain the isotopic similarities if they formed in a very similar environment. But also, this model turns out to be difficult to explain dynamically. The last one is the fission hypothesis. So according to this model, the small lunar iron core can be explained because the moon is made of the earthy mantle materials. But it cannot explain the volatile depletion, but it can explain the isotopic similarities. However, this model requires a very fast spin of the Earth, which is not consistent with the current angular momentum of the Earth-Moon system. So all of these hypotheses were rejected. So after the Apollo missions, scientists proposed a more energetic model. This is called the giant impact hypothesis. So they thought that there could have been a collision between the Earth and a Mars-sized object. So this energetic event could have homogenized the Earth and also the impactor materials. So according to this model, Earth was hit by a Mars-sized impactor and that formed a disk around the planet. And the disk had a very high temperature, therefore it was partially vaporized. So this vapor is made of silicate, and the moon accreted from the disk. I'm going to show you a simulation. So this is the impactor on the left and the Earth on the right. And the color, reddish color to yellow color shows the entropy, which represents the extent of shock heating, and the gray shows an iron. As you can see, the surface of the Earth is highly shock heated, and the impactor hits the Earth a couple of times, and the impactor is completely destroyed by the impact itself. And as you can see, during the impact event, the core of the impactor is falling onto the Earth. As a result, there is not much iron left in the disk. Therefore, this can explain why the moon is depleted in iron. So this model has been favored for many reasons. So first of all, as I mentioned, this can explain the small iron core of the moon, and this can explain the Earth-Moon angular momentum. It can potentially explain volatile depletion. Some volatiles could have been lost during the impact event, but it turns out that the isotopic similarities are not easily explained. Let's look at the same simulation with different colors. Now, the blue particles represent materials coming from the proto-Earth, and the yellow particles represent materials coming from the impactor. So as you can see, most of the disk materials are coming from the impactor. Since the moon are created from a disk, you'd think that the composition of the moon should be similar to the composition of the impactor. And unfortunately, we are not able to mix the impactor and the proto-Earth materials. It is expected that the impactor had different isotopic ratios from the Earth. This model cannot easily explain why the Earth and the Moon have very similar isotopic ratios. To solve this issue, new models have been suggested. One of them is the fast spinning Earth model. So in this model, the Earth was spinning very fast and had an oblate shape like the figure, and it was hit by a small impactor. And they stripped off the outer part of the Earth mantle and from the disk, and the Moon accreted from the disk. In this model, the Moon is coming from the Earth mantle, therefore the isotopic similarities can be explained. And more recently, the group extended their model. So this is called the synestia model. So this is a more generalized model that includes high energy, high angular momentum impact event. So in this case, the disk has a very high temperature and it's connected to the Earth. And the disk is convecting vigorously. Therefore, any pre-existing isotopic heterogeneities could be erased. The next one is a half-Earth model. So in this model, there was a collision between two half-Earth-sized objects, and everything was mixed together, and therefore the Moon and Earth would have had the same isotopic ratios. So the next one is a multiple impact model. So according to this model, the Moon formed by multiple impacts instead of one single impact. A small impact that hits the Earth and that forms a small disk, and the moonlet accretes from the disk, and another small impact that hit the Earth and form another moonlet. These moonlets accrete to a single body. If the speed of the impact is high enough, it can strip off some mantle materials. Therefore, the Moon could have made of the Earth's mantle materials, which can explain the isotopic similarities. The next one is the magma ocean model. So according to this model, the surface of the Earth is covered by a magma ocean, and during the impact, the magma ocean preferentially removed and launched to the orbit. As a result, the Moon is primarily made of the Earth materials. So I just want to show you some other simulations just for fun. So this is a fast spinning Earth model, and then you can see that the Earth has an oblate shape. So you can see that outer part of the Earth mantle is stripped off, and also you can see that this is a more energetic impact model than the standard model. So the second one is the half Earth model. So these two bodies are colliding with each other a couple of times, and this is also a very energetic impact event. And any pre-existing heterogeneity could be erased. Okay, so let me summarize up until here. So far we talked about the standard model, magma ocean model, multiple impact model, and half Earth model, and the fast spinning Earth synestia model. The three models can explain the isotopic similarities, while the standard model and the magma ocean model may have a challenge to explain the isotopic similarities. But it is possible that the impactor had the same isotopic ratios to the Earth. So this idea has been explored recently. It turns out that we have additional constraints. Volatile depletion is one of them. So the Moon may have lost its volatiles during the accretion phase. The second one is the small isotopic differences. Due to the recent advancement of analytical capabilities, nowadays we can resolve very small isotopic differences between the Earth and the Moon. Some of the isotopic differences would have formed during the accretion phase, but some others may be suggesting that the Moon still has the memory of a small impactor component. The third one is the unmixed mantle. Geochemical studies indicate that the Earth's mantle was never mixed. So here is the list of isotopic systems, and some of them may have formed after the moon-forming impact, while some of them formed prior to the moon-forming impact. So this indicates that even though the moon-forming impact was such an energetic process, it didn't completely homogenize the Earth's mantle. So this needs to be consistent with the impact model. So we don't really know the location of the mantle heterogeneity, but they could have existed at the core mantle boundary. So the last one is the angular momentum constraint. So if you assume that the Earth and the Moon's angular momentum has been conserved and bring the Moon back much closer to the Earth, the initial length of the day of the Earth is around 5 hours. So this is very fast. But in a fast spin-Earth model, Harker's model, and Synestia model, the length of the day is actually much shorter, around 2.5 hours. So this is because at the end of the simulation, the angular momentum of the Earth-Moon system is much larger than the current value in these recent models. So these studies indicate that the angular momentum between the Earth and Moon could have been transferred to the Sun-Earth system. Therefore, the angular momentum of the Earth-Moon system was not conserved. So this is a very active area of research, and we are figuring out whether it is possible to remove the right amount of the angular momentum from the Earth-Moon system. Okay, so this is my quick summary. So the scale is shown on the right, and so I'm trying to be as objective as possible, but I'm sure not everybody in the community agrees on this panel, but this is my take. So first of all, I would like to mention that so we still need to understand the small isotopic differences and also the volatile depletion. So this depends on the Moon accretion process, which is poorly understood. So this is a homework we have to work on. For the standard model, the isotopic similarities may be difficult to explain, but if the impactor had the same isotopic ratios, that could be a solution. For the standard model, the mantle doesn't get mixed by the impact because even though this impact is very energetic, it's less energetic than the other models. And this model doesn't require removal of the angular momentum. For the multiple impact model, this requires a collection of specific impacts, so that could be a bit of a challenge. But each impact is not very energetic, so the mantle remains unmixed, and also angular momentum is probably okay. So for the Earth model and fast spinning Earth Synestia models, the isotopic similarities can be easily explained, but since these are very energetic impact events, the unmixed mantle can be difficult to explain. Also, these models require removal of the angular momentum, and the process has been still unconstrained. This is an important problem to solve. Okay, so the next question is, when did the Moon form? Here we take 0 as the solar system formation time, which is around 4.57 billion years ago. And different arrows represent different isotopic systems and also modeling approaches. As you can see, there is a wide range regarding the age estimates for the Moon. but the typical formation age estimates range from 60 million years to 100 million years after the solar system formation. Okay, and also the moonfall impact has implications for atmospheric loss. So originally, we thought that the Mars-sized impact would have stripped off the entire Earth's atmosphere. But more recent studies indicate that actually a large fraction of the atmosphere would have survived. So the detail depends on the model, but about the 60 to 38% of the atmosphere will be lost. In other words, majority of the atmosphere can remain on the Earth. And also the presence of an ocean enhances atmospheric loss. But the another key point here is that the amount of the lost atmosphere depends on the model. Energetic impacts can lead to the atmospheric loss. So you can see the figure at the bottom. So x-axis is the impactor velocity divided by the escape velocity times impactor mass divided by the target mass. And the y-axis is the fractional atmospheric loss. So as you can see, for the standard model, the loss is around just 5% or so. But for the hard Earth and Synestia models, the loss could be almost 100%. So different lines represent different models. So as you can see, the survival of the atmosphere is very model dependent. The impact could have affected the behavior of carbon, nitrogen, and hydrogen. So first, let's look at the figure on the left. So this shows the bulk Earth elemental abundances normalized by the CI chondrites. So chondrites are supposed to be building blocks of the Earth, and CI chondrites are the most primitive ones. And we know that the silicate portion of the Earth has an elevated carbon-nitrogen ratio compared to chondrites, CI chondrites. And this could have caused by a large impact. So one of the new studies indicates that the nitrogen could have delivered to the core of the Earth. And this could explain the elevated CN ratio in the silicate. But other explanations exist. Perhaps this could have caused by atmospheric loss, or maybe our assumption that the building blocks of the Earth was chondritic was wrong. Perhaps the building blocks had a different CN ratios than the chondritic value. Also, most of the water was thought to be delivered prior to the moonfall impact. This is to explain the non-chondritic NH ratio. After the moonfall impact, some asteroids delivered some materials to the Earth, but these asteroids would have had the chondritic NH ratios. Therefore, any later addition cannot change the NH ratio. Therefore, non-chondritic NH ratio would have been established prior to the moonfall impact. I'd like to quickly discuss Earth's evolution. Right after the moonfall impact, the Earth's surface was very hot, and we had a silicate vapor atmosphere, and the Earth would have had a deep magma ocean, and part of the Earth's mantle may have remained solid, and perhaps at the bottom of the mantle there might have been a heterogeneity. Within 2 to 10 million years after the moon forming event, the Earth established a much nicer environment for life. So atmosphere would have been made of water, CO2, and some other vapor, but the details depends on the accretion process. And there could have been ocean on the surface, And it is possible that at the bottom of the mantle, there was a basal magma ocean. I'd like to discuss Hadean tides. The tidal height is proportional to a to the minus third. Here A is the lunar major axis, meaning the distance between the Earth and the Moon. Assuming that tidal height of today is 0.5 meters, tidal height would have been more than 100 meters when the same major axis was around the 10 Earth radii. Here the symbol R means the radius of the Earth. So this would have happened around 1 to 10 million years after the moon formation. And the tidal height would have been around 2 meters when the same major axis was around 40 Earth radii. This would have happened around 10 to 100 million years after the moon formation. And according to one of the studies, the tidal heating may have kept Earth a bit warmer, about by 5 degrees or so in the first 100 million years or so. So this could have been quite important for life on the Earth's surface. The presence of the moon affects the stability of the Earth's spin axis and its climate. So the Earth's spin axis is tilted. So this it's called obliquity, and this obliquity is around 23 degrees today. And we know that the presence of the moon is helping stabilizing the Earth's spin axis. So when you look at Mars, the Mars obliquity can change from 0 to 60 degrees. So this is a very big change, and this affects the Martian climate cycle. And a previous study indicate that without the moon, the Earth's obliquity could change from 0 to 85 degrees. This is a big change, and this can affect the climate on the Earth. People thought that to grow any intelligent life on the planet, you have to have a moon. But the more recent study indicates that the Earth's obliquity would change from 20 to 25 degrees without the moon. So this is still worse than the current obliquity change, but this is not as chaotic as previously thought. And the stability depends on many factors, including initial obliquity, mass ratio. So this is a very complex problem. I'd like to discuss exomoons. Exomoons are moons around the planets in extrasolar systems. Despite extensive searches, there is no confirmed exomoon to date. This is quite surprising because planetary impacts are very common during the planetary accretion phase. Therefore, you'd expect that the exomoons should be everywhere. So this could be potentially explained by observational bias. These extensive searches are primarily based on the Kepler Space Telescope data. And the Kepler Space Telescope find planets that are close to their host stars. These planets cannot have stable moons for a long period of time. So this could be an explanation. But I'm hoping that we are going to find an exomoon very soon. In summary, the scientific community agrees that the moon formed by an impact, but the details are actively debated. We need to make stronger connections between models and observables, including volatile depletion and isotopic ratios. Each model has different implications for atmospheric loss, chemical compositions of the Earth's core and the mantle. Presence of the moon affects tides and stability of climate. Exoplanets with exomoons may be good candidates to host life because the moons stabilize the exoplanetary spin axis and its climate. But no exomoon has been confirmed to date, but stay tuned. This is the end of my talk, and thank you very much for your attention, and I'm looking forward to seeing you all very soon.